Chapter 3.6, Implicit Differentiation. When you hear implicit differentiation, you probably don't quite understand what it is. But basically, it's just finding the derivative of equations with two variables rather than just one. So originally, we've been finding the derivatives of equations such as y equals 2x or something like that. But now, we have both variables, as you can see, so you have to take both of them into account. When finding the derivative of a regular equation with only one variable, all you really have to remember is that you have to multiply by the exponent and then take it down a power. But when you have an equation with two variables, you have to do that for x, but then you have to remember that y becomes dy over dx whenever you're going to take the derivative of it. So for example, if you're going to do y squared, such as here, you have to multiply by the exponent and then take it down a power, but then you also have to attach this dy over dx. And you have to attach dy over dx whenever you do implicit differentiation. So how do you do implicit differentiation? Step 1, you have to differentiate both sides of the equation with respect to x. And then, for step 2, you have to solve for dy over dx by collecting terms and factoring. Now right now that may not make a whole lot of sense, but as we do some examples later, hopefully it'll start to make a lot more sense. Now that you've heard the steps for implicit differentiation, let's try to find the derivative for this equation. Step 1, if you remember, says differentiate both sides of the equation with respect to x. Let's start out by just trying to work on the left side alone. To find the derivative of this, you have to take it like you normally would and multiply by the exponent and then take it down a power. But when you have y's here, you have to also take it times dy over dx. And then when you find the right side of the equation, it's all x's, and since we're differentiating with respect to x, you just do to find the derivative normally. So that'll come out to be 2x plus 5. Now for step 2, it says solve for dy over dx by collecting terms and factoring. So that might seem a little weird, but what it's basically saying is that it wants you to get dy over dx all by itself on one side, with the rest of it on the other side. Now this is just basically a multiplication problem on this side. So all you really have to do is divide by 2y on both sides. As you can see, that got dy over dx all by itself, with 2x plus 5 over 2y on the other side. So 2x plus 5 over 2y is the derivative of your original equation, y squared equals x squared plus 5x. Now that we've done an easy problem to help you get the general idea of how to do it, let's try a harder one. So right here we have x cubed minus xy plus y squared equals 4. And the first step says to differentiate with respect to x, which is usually pretty easy. But in this problem, we have the dreaded product rule. So we can start by just doing that off to the side to get it out of the way. Now the product rule says that you want to take the derivative of the first plus the second, and then you have to add the derivative of the second plus the first, or vice versa. Because it's addition, it doesn't matter which one you do first. So let's start out by doing that. You can take the first one times the derivative of the second, and because it's y, it just has to be dy over dx. And then you have to add the second times the derivative of the first, but the first one is just x, and the derivative of x is 1. So it'd just be times 1, which is the same thing as y. Now let's do the rest of the problem down below. When you differentiate it all, it becomes 3x squared, and then you have to remember this part, so add that in, and it has a minus sign here, so you have to make it all negative. So it's minus x over dy over dx, and then minus y. And then for this last part here, you have y squared, which becomes 2y, and then you can't forget the dy over dx, and then it all equals 0 because the derivative of a constant is always just 0. Now we have to take into account step 2, which says solve for dy over dx by collecting terms and factoring. And in a problem like this, where you have more than one dy over dx, that's where that really comes in handy. So what you want to do is get all of that on one side. So how we can do that here is by adding it to the other side, or subtracting. So we'll have 3x squared minus y equals x over dy over dx minus 2y dy over dx. And then as you can see on this side, both of the two parts of the right side of the equation have dy over dx in them. So you can factor them out, and that becomes dy over dx times x minus 2y. And then you have yourself a simple problem again, where you can just divide by this part to get dy over dx by itself. So let's do that here. After you divide by x minus 2y, you get the final answer of 3x squared minus y over x minus 2y equals dy over dx. So that is your final derivative of x cubed minus x times y plus y squared equals 4. You can also do implicit differentiation for equations that have cosine or sine or things like that in them. Let's try it here. So once again, the first step is that you have to find the derivative of the whole thing. So the derivative of x is just 1, and the derivative of cosine is negative sine y, but then you have to take into account the dy over dx again. So the next step is that you have to get this part all by itself. So once again here you can just divide by the other part. So you'll divide by negative sine y on both sides, and you'll end up with 1 over negative sine y equals dy over dx. But if you look around here, you'll see that you have 1 over negative sine y, which is the same as negative cosecant y. So that ends up being your final answer for that problem. Not a hard problem, but you just have to remember that you can do it also with cosine or sine or something like that. So now we've gone through a few examples, and really all you have to remember when thinking about implicit differentiation is that you have to differentiate all of the parts of the equation with respect to x, and then collect and factor the dy over dx's. And now that we've spent all that hard time learning about implicit differentiation, here's some track pictures for your enjoyment.